The ghostly glow of a nuclear power station was detected in pure water 150 miles away. Back in 2018, a tank of the purest water, buried under kilometers of rock in Ontario, Canada, flashed as barely detectable particles slammed through its molecules. It was the first time that water has been used to detect a particle known as an antineutrino, which originated from a nuclear reactor more than 240 kilometers away. That's 150 miles away. This incredible breakthrough promises neutrino experiments and monitoring technology that use inexpensive, easily acquirable, and safe materials. As some of the most abundant particles in the universe, neutrinos are odd little things with a lot of potential for revealing deeper insights into the universe. Unfortunately, they are almost massless, carrying no charge, and barely interact with other particles at all. They mostly stream through space and rock alike, as though all matter was incorporeal. There's a reason they're known as ghost particles. Antineutrinos are the antiparticle counterpart to neutrinos. Usually an antiparticle has the opposite charge to its particle equivalent. The antiparticle of the negatively charged electron, for example, is the positively charged positron. Since neutrinos don't carry a charge, scientists can only tell the two apart based on the fact an electron neutrino will pop into existence alongside a positron, while an electron antineutrino appears with an electron. Electron antineutrinos are emitted during nuclear beta decay, a type of radioactive decay in which a neutron decays into a proton, an electron, and an antineutrino. One of these electron antineutrinos can then interact with a proton to produce a positron and a neutrino, a reaction known as inverse beta decay. Large liquid-filled tanks lined with photomultiplier tubes are used to detect this particular kind of decay. They're designed to capture the faint glow of Cherenkov radiation created by charged particles moving faster than light can travel through a liquid, similar to the sonic boom generated by breaking the sound barrier, so they're very sensitive to very faint light. Antineutrinos are produced in prodigious quantities by nuclear reactors, but they're relatively low energy, which makes them difficult to detect. Enter SNO plus, this is where we get this image from, buried beneath more than 2 kilometers of rock, that's 1.24 miles of rock. It's the world's deepest underground laboratory. This rock shielding provides an effective barrier against interference by cosmic rays, allowing scientists to obtain exceptionally well-resolved signals. Today, the lab's 780-ton spherical tank is filled with linear alkyl benzene, a liquid scintillator that amplifies light. Back in 2018, while the facility was underdoing calibration, it was filled with ultra-pure water. Combing through the 190 days worth of data collected during that calibration phase back in 2018, the SNO Plus collaboration found evidence of inverse beta decay. The neutron produced during this process is captured by a hydrogen nucleus in the water, which in turn produces a soft bloom of light at a very specific energy level, 2.2 mega electron volts. Water Cherenkov detectors generally struggle to detect signals below 3 mega electron volts, but with water-filled SNO Plus was able to detect down to 1.4 mega electron volts. This produces an efficiency of around 50% for detecting signals at 2.2 mega electron volts. So the team thought it was worth their luck looking for signals of inverse beta decay. An analysis of a candidate signal determined that it was likely produced by an antineutrino with a confidence level of 3 sigma, a 99.7% probability. The results suggest that water detectors could be used to monitor the power production of nuclear reactors. And meanwhile, SNO Plus is being put to use to help understand neutrinos and antineutrinos better, because neutrinos are impossible to measure directly. We don't know much about them. One of the biggest questions is whether neutrinos and antineutrinos are the exact same particle. A rare, never-before-seen decay would answer this question. SNO Plus is currently looking for this decay. It intrigues us that pure water can be used to measure antineutrinos from reactors and at such large distances, said physicist Logan Lebanowski of SNO Plus Collaboration and University of California, Berkeley, back in March 2023. We spent significant effort to extract a handful of signals from 190 days of data, and the result is gratifying, he said. The research is published in Physical Review Letters. This version of the article was first published April 2023, and this is on Science Alert by Michelle Starr. Please leave your comments, and thank you for your support. Please support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.